Hello everyone. Welcome to Tolerance Stack-Up's 501, Going Beyond Mechanical Fit and into Predictive Design, brought to you by Fictiv. I'm Carlos Gonzalez, Special Projects Manager with Mechanical Engineering Magazine and ASME, and I will be your moderator for today's event. Before we get to the topic, let's get some simple housekeeping items out of the way first. The console you are looking at is completely customizable. From the presentation window to the Q&A panel, every window you currently see can be moved, enlarged, or collapsed. So if you want to change the look and feel of your console, go right ahead. We would like today's webinar to be as interactive as possible, so please feel free to post your questions and comments throughout the presentation. If you have a question for our speaker, please enter it in the Q&A widget. We will get to as many as we can during the live Q&A session at the end of the event. If we don't get to your question, you may receive an email response. Also, a reminder about our giveaway for today. One lucky attendee will win a 31st edition of the Machinery's Handbook. We'll be doing a random drawing after the webinar, and we'll contact the winner for more details. For more information on this topic, make sure to check out our resource modules where you can download related materials. If you need to leave early for any reason, don't worry. The presentation will be recorded and available for on demand. Now let's get to today's topic. Our presentation today comes from Fictiv, a digital manufacturing ecosystem that rapidly delivers custom mechanical parts on demand through its quote-to-order platform and a global network of manufacturing partners to help engineering teams accelerate new product innovation. Fictiv offers a wide range of flexible manufacturing options through a single platform, including CNC machining, 3D printing, urethane casting, injection molding, and a wide range of post-processing options like metal finishing, hardware installation, and advanced quality inspections. Today's presenter is David Cagle, a senior mechanical applications engineer from Fictiv. David is a highly experienced design engineer with a demonstrated history working in the aerospace and medical device industries. He has built over 1,000 CNC parts, 500 plus injection molded parts, and holds over 18 patents and counting from his Pratt & Whitney, Johnson & Johnson, and Verb Surgical work experience. Today's agenda will cover tolerance stack-ups and why they are a vital component of any engineer's workflow. In demanding industries such as medical, aerospace, and automotive, engineers must provide a better design beyond the basic guess and check. They are expected to improve design understanding and better forecast predictive design metrics. Today's webinar will elevate your design process to the next level by using tolerance stack-up analysis to identify critical dimensions and risk-based decision-making. Again, thanking you for joining us today. David, the floor is yours.
Hey, Carlos, thank you. So just took over control here, and I believe I am presenting, and so I'm going to go to the next slide here. And we're just going to go over very quickly with a quick poll here, and just for me to understand where the audience is at and what your experience is with tolerance stacks. So if everybody could take this time right now and just kind of select one of the options for me, and we'll review the results here. And as you can play the Jeopardy music in your head, I need to take control. I am in control. There we go. Sorry about that. So like I said, we are taking a poll real quick and asking that you go through and kind of tell me what your status is on your tolerance stack experience. And then in 5, 4, 3, oh, I actually have a timer up there. 3, 2, 1, I'm going to review the results. Okay, so from the look at the results here, thank you for everybody who voted. There's some familiarity with it. There's some I've done it in school, totally new, and a couple people saying they're a pro. Great. This helps baseline where I'm going to go, and I think with the majority of people being kind of in the categories 2, 3, 4, that this will be very informative for you. For those that this is totally new to you, there is other subsequent or supplement information for you to dive in. And as you take notes and say, hey, I'm not sure what you meant by this, feel free to either ask and I can point you to that subsequent material as we proceed forward. So, quick refresher that I want to just go through. This should be very familiar with many people, but what is a tolerance stack, right? So looking at what is a tolerance stack, you are taking your parts and you are trying to establish a mathematical model for how they all fit together. And these are usually done in what's called the tolerance chain or a tolerance loop. And you establish a direction, usually left or right. You pick at the very beginning is positive. And as you go through your assembly, you are establishing direction and the magnitude of that via your tolerances. And you add them all up together and you're trying to figure out what is my gap, G there in the image on the right, or what is my interference. For the predominant or majority of this presentation, I'm only going to be referring to RSS root sum squared tolerance stack up. And if you have more questions about that, there is a subsequent and supplement article that goes super in depth about it, and you can nerd out on that on your own. But going forward, the reason we're doing RSS is because a tolerance stack or spreadsheet is kind of readily available to everybody as an engineer and doesn't really require any other supplemental tools to purchase for your organization. And next slide. And then if you see me looking away every once in a while, I have notes here on the left-hand side, so I'm going back and forth. So a quick overview of the process of what we're about to go through. I've kind of outlined 6 steps of what we're going to do and how you start to do your tolerance stacks. And what's really important to notice or to think about as you are the working engineer is that you may not always be starting at step 1. So yes, this has been put into a linear line so it fits on a screen for us since we're all confined via Zoom. But ideally, this is a full circle and you may drop in at step 3. You may drop in at step 5. It just depends where you are in your development cycle. But the whole process and the whole loop, just like the tolerance stack chain, right, is what's needed to really achieve your end results. So going through the steps fairly quickly here, because you guys can all read the slides. First step is define interactions and states of your device or your mechanism. Examples of this would be button press, button not press. Determine the output. What are the criteria that you're looking for to measure? Maybe it's a spring, right? My spring needs to be compressed this far to exert and output the required force, but it needs to not go this far or it will yield. Laddering straight into that, determine your potential failures. What happens if the spring does not exert enough force? What happens if the spring does fail and yields? This leads into what hazardous situation does this cause for my product, my user, anybody, right? And then you use those bits of information to determine what your stack limits are. And then it's only step 5 really is where you're actually doing the calculation in the loop. And lastly, based on all of this information, you're using the mathematical model of the tolerance stack that you created to determine what your CPK is and evaluate, do I need to make a design change now, or do I need to put in further control measures to try to control my risk? And then feel free to ask questions, raise your hand, or however that is. I have a bunch of different people assisting me on this. So if they have any questions, they'll also ping me directly too. Great, cool. So moving on to the next slide. So one of the things that you have to do when you first start doing your tolerance stack is kind of decide where to start. So I went on to GrabCAD and grabbed a linear rail example and kind of said, like, if I had to do tolerance stacks on this, what would I do? And one of the first things I do is I go and I break it down into subsystems. Where are groups of parts that I can collate together and separate them out from the different groups such that I can start breaking a large problem down into an actionable thing that I can do right now. So first step, as you can see here, I went through and just kind of said, all right, I'm looking at this. It looks like I have a carriage. I have some rails. I have some proximal assembly with a motor and belt, and then I have a distal, and then I have like this whole side electronics portion of my assembly. So after I've broken that down, you're now kind of exploding it, and what you're looking for are the interactions. So there are many ways of doing this, and you could just grab and start pulling your CAD apart like I did in the top image. And there's also the ability to kind of use and utilize SolidWorks Auto Exploder and using that and seeing where all those yellow lines are. And so the reason we're going for these interactions is in those interactions, somebody in the CAD has spent time to mate them and put them together and do all of the controls via CAD, but it's also telling you that there's likely a tolerance spec that is in that interaction. So if I go through and I were to do kind of a DFMEA line slice approach where I cut the line, I look at those parts and I say, what could happen here? Are there parts that need to go together? Are there parts that need to perform together to get my desired result for my design and or device or interaction to work? And so as you can see, up in the top right-hand corner of all my slides, I've kind of added what step we're in. Ideally, like I said, you want to go 1 through 6, but that's not how the real world really works. And in some of these, I will be jumping around outside of sequential order, but it's because I'm explaining something in the future such that it makes sense why you're doing it now. Great. So once you've kind of broken those subsystems down, you kind of go through your, hold on. Okay. So I'm going to actually jump down to slide 13 first. So when you go through this, you go through and after you've broken it down into subsystems, you can see that you can grab certain features and take a cross section inside of your CAD, take your screenshot, and then you kind of just go through and you start circling your interactions, right? I say, hey, like this looks close, and I put a circle and I label top rail 1, and I see something else, and I kind of just keep adding the circles, and I'm just investigating what things am I seeing on my screen that I should take a closer look at. And after I've done this, you go back and you start listing these out in a table format. And inside of this table format, I kind of list out what my tolerance stack, what the description was of what I was looking at in my image, and then what are the potential failures. And so then on the right-hand side, there you see something that says, what is the tolerance stack CPK? We're going to get into that later, but it's very important to start what I call is this tolerance stack scorecard. And this is basically, like I said, a running list of all of the things that you're looking at, have looked at, or want to look at. And you describe it, and then you also say, what are my limits? You're going to be missing portions of this if you do not think about what could go wrong. So not only you're looking at it for a reason, why are you looking at it? And then once you're looking at it, what are those failures? If it's, as you can see in my example of like thin width too wide, the fin wouldn't fit inside the top rail groove, causing grinding on the rail chassis base. If it was too narrow, not really applicable. So back to what is CPK? So CPK is like a statistical term where it's kind of telling you what the processes are capable of doing in the future. And so when we're doing our tolerance stacks, we are going to be setting the upper spec limit and the lower spec limit for the ranges of our design or the ranges of the part inside our tolerance stack that are going to convey futuristically how we believe our design is going to perform. Okay, I'm not going to get into the difference between PPK. You can dive more into that later. Like I said, this is a slide again of our cross section where we've gone into the carriage, we've taken a cross section, and then we've investigated the interactions in between these subassemblies. So back to CPK and determining what it is. For very quick layman's terms on CPK, think about just parking your car inside a garage. And a CPK of less than 1 means that you are not capable and that the design will not really function as you're anticipating, or you would basically run your car into the sidewall. It's capable, but not centered would be around a CPK of 1, where you're going in, but a mirror is basically infinitely touching the sidewalls. And then a CPK of something like 2 means that you could be, either your car could be twice as wide, or you could be almost half off of the center line of your garage, but you would still go within the walls of your garage. I'm trying to make sure we don't have any questions at this point. These are very quick definitions. But if you do have any questions, feel free to keep blowing up the group chat, as I see many people are doing. So why did we just spend this time on CPK? So what's important to understand for your CPK, check the questions and answers box as well. Sorry, I'm talking to myself. There we go. Cool. Let me rearrange real quick. Sorry guys, this is new software to me as well. Just arranging real quick. Okay, thank you. So the reason we're addressing the CPK, because this is part of your futuristic heuristics of what the design will be capable of. And when we're doing that, it's very important. Is always your future is also related to risk of what could go wrong, how probable is it, and how am I controlling it. So this is super popular in both aero and medical. And part of this has to do with kind of the risk hazard zones. So one of the examples of what you want to do when you're talking about things of, will this fit, will this not fit, if the spring is too compressed, if the button does not fully depress, what happens? So here there's a very quick table that you can use of the different definitions of occurrence rate, which is across the top, probable, low, very low, remote, improbable, and then the severity, catastrophic, critical, serious, moderate, minor, or negligible. So what's really important to understand in this graph is that you're using the combination of both items to determine what risk factors or what risk zone you're in. It's very important here to notice that this is just a depiction of my understanding of this, and that these categories and the way the red, yellow, and green boxes can shift are dependent on your own company and or the industry. As an example, catastrophic in aero is considered like the whole airplane goes down, and that you could face mass casualties if something like this happens, right? So that would be, even at a very, very low probability, you could still end up in a catastrophic or very high risk red zone territory. Critical would be the unfortunate event of somebody like a death. Serious is irreversible harm. Moderate could be something as like you pinch somebody or they get a cut, etc. Minor is an example of like a two-part fit, where it's just the parts don't fit together. Your manufacturing team might be annoyed, and it might cause scrap, but it is minor relative to the big picture. Negligible, no harm, that would be something like you end up with a scratch on a part or something. Next slide. Okay, so once again, going back to like how I was jumping out of order. So how does that risk hazard relate to the probability of your risk? So here, what I'm trying to do is use CPK as a method of controlling that risk hazard. So when I'm targeting CPKs, it's always desirable to be 2 or greater, right? That's the dream. That's your 6 Sigma best practices. But that's not always reasonable, or not always reasonable to do in the amount of time that you're being given. So as you're going through and you're looking at this, you are taking that risk hazard and you're taking the top line there in my table of critical, serious, moderate, minor, or negligible, and you're saying, okay, if I have a moderate condition and I want to basically eliminate this error, what CPK would give me an acceptable thing to move forward with my project? And doing that, this chart kind of tells you for a moderate item, you can go to a CPK of, if you can calculate a CPK of 1.67 or higher, that you have probably adequately controlled your design. And you can move forward and say, this thing is green, move forward. As you can also see that there are different options in these legends, where green is, or the teal is kind of acceptable, yellow is as low as possible, orange is team review, and red is cross-functional review. And what these different categories are acceptable is, that's just like a broadly accepted, this is, we know it's a risk, but we have mathematically determined it is low. as low as possible. This used to be previously as low as reasonably possible in the medical world, and they changed that. So you might also hear this term defined as ALAP. These are ranges of where you fall. And inside each of these boxes, you see that I have different numbers, and there's like 25 to 35, 15 to 25, etc. These are suggestions for if you were to use more advanced statistical tolerance stack software, where those reports will actually tell you, hey, this single dimension derives 25 to 35% of the variability of your tolerance stack. If a single dimension falls on this table, then this would immediately let you know, like, hey, I should make this a critical dimension. This should be an inspected dimension on my drawing and in my quality control plans, such that I am harnessing, governing, and attempting to measure the outputs of even down to single parts to make sure I get an acceptable output of the performance of my device. That was a lot. So if you're following me thus far, or if you have questions, feel free to continue to write them down, ping the inbox, and we'll continue to answer them. So thus far, what I've been trying to lead you to is, how do I take my assembly, kind of break it down into subsystems? What do I look at? And then when I'm looking at those, how do I associate what I'm looking at and my basic math models to the risk? And then how do I take that risk and say, what type of statistical CPK gets me to a level where I, with confidence as the engineer, as a team of engineers, can say, we believe we have a handle on this situation. And so what's important is, if you get into the red zones or the orange zones, is your communication to your other teammates, right? And because what happens ultimately is, ideally, you, the engineer, want to control as many of the risks that you have on your drawing and through your testing, right? So risk is managed with, you either do some type of engineering hand calc, you do a simulation, or you do some type of test. Sometimes you do all of them, right? And if you can get things boiled down or de-risked with simple tolerance stacks, you're going to push your entire project a lot further ahead and be more advanced if you do this method. All right, I'm going to review some stuff here real quick. We'll get some of those questions later. Okay. If you join the webinar, there is a tolerance stack spreadsheet that's available for download. Inside of it, you can go through, you can start working on it, start adding images, pictures, etc. But what we're really going to do is dive straight into like a real life example of something that I did with a partner that has been working with Fictiv. So on this next slide, the real world example is a portable bidet device that I'm working on with a client called Sunny. He's probably on the call here at some point. But in this first real world example, I'm doing something simple, and this is really happened, right? This is real. Basically, the failure that we were experiencing is that the canister that holds the water to slide into the device wasn't going in smoothly, or wasn't going in deep enough to engage with the pump mechanism. So when we look at that, I've gone through and I've kind of taken a screenshot, made a quick little GIF, and said, here's my interaction. I'm determining the output. The output is it needs to slide in fully, engage with the pump. And then the potential failures of this are, hey, it basically renders this device fairly useless if the pump doesn't have access to the water. It just won't work. So I go through that and I say, man, that's fairly severe. If it yields the device, it won't work, then we need to understand that. So one of the first steps that I did was I went through and I looked at the canister that was comprised of several parts and how it was sliding into the main chassis. And as you can see, that there was a main body, there was a collar, and then there was a cap that pivots on a pin. And I go through this tolerance stack and I list out, hey, what is my part description? It's the canister collar, the flat on the bottom on the button side, to the dowel hole center. And so I'm defining my loop and I'm drawing with arrows, I'm putting numbers on all of these dimensions, and I'm adding them into my tolerance stack spreadsheet. And so as you can go through here, you can see that I'm also documenting like, hey, where did I find this on the drawing? So one of the things that is differentiated about Fictiv is we accept your drawings, right? And the reason we accept your drawings is I know and we know that this information is important, that some of these tolerances and the things that you need for your parts are critical to the function and the performance. So here in this image, what I was defining with my purple arrows is there is a theoretical world where, based on the tolerances of this part, that the top cap could actually stick out or to the right of the flat of the item that was sliding into our aluminum chassis. So I'm going to go back to here and show you that again. So here on the left-hand image, you can see the cap has been open where the water is being poured in. On the right in the GIF, it's been closed and it's sliding in. So if you can imagine kind of when you Russian doll nest assemblies, right, you can end up with a Leaning Tower of Pisa type of interaction where one part based on the two-part fit on the inside is now shifted to the left, and then based on the other fit on the second one, it's also shifted to the left or the right. So you can end up with this skew of the parts falling outside the boundaries. And one of the common things in the, I don't know if it's a technical term, but what I've heard it referred to is datum confusion. That when you're making your assemblies and when you're trying to assemble things together, you want a bare minimum number of parts interacting and guiding your assembly. So, sorry, reading a quick chat there. So when you do this, you're trying to make sure that one feature is your guider and that you're not having multiple features compete with each other for which one is the interaction plane. You can digest that a little bit. That's a very important design criteria, and that is really one of the things that you're trying to flush out in many of your tolerance stacks. What is supposed to mate with what is supposed to purposely touch something else, and what should I just get away from? So here in this thing, you can see after I've calculated the tolerance stack loop and put all of the things in, what's important is that your nominal here on the bottom left in the results there, that should match your CAD. So one of the important things to do when you're doing your CAD setup is to model things as you expected them to be. There's many different methods, especially on like precision gear fits, etc., precision bearing fits, that you may not do this, but in many devices, it is very important to model your extremes as you expect them. Because this, when I do my tolerance stack and then I measure my nominal and it matches, I know that I've basically created and or completed my tolerance stack correctly. My CAD is matching my numerical, so I know that I'm doing this correctly. Now, the max and min that are in here are based on the specifications of your drawing tolerances that are on your drawing. And then sometimes you don't have these, you're making them up. So if you were to go to Fictiv's site on tolerances, there is a huge page with a whole bunch of drop downs for what is acceptable in the different ranges. And it's really important for you to notice that if you were to go that, and as you do these, holding plus or minus 1 thou on everything is not necessarily where you want to be. You want to be balancing this and trying to open up the dimensions as much as you can, and that will get you to your CPK results. So kind of related this and went through this in fairly good detail, but the next step is really what gets you into your predictive design. So after you've gone through your tolerance stack, you've gotten these results, you're getting to what are the limits. So here, it's very important when you say, when you're setting up your limits, that you understand that there is a upper spec limit and a lower spec limit. And the resulting CPK is whichever is lower of the two. So if you were to go in the spreadsheet, I've figured that out for you. The equations would just work for you. So what's also important as you're assessing these limits is that you don't bring in outside contributors of, well, what about this if this happened and that could happen, right? You're trying to boil it down to a single statement, right? Of if you go back to, let's go back to my image here, up one. If this gap is greater, or is 0 or negative, what happens? So I come back to this, push the audience, right? And say, hey, my lower spec limit is 0. Theoretically, if this were 0, the device would still ride on this flat. And what I'm looking for is that I don't want this part or this part to stick out below this flat, because I want this to slide directly in. Okay? So theoretically, as long as this tolerance stack is not negative, that device or the interaction that I'm looking for should work. So how about the upper spec limit? The upper spec limit in this case, it theoretically doesn't matter, right? If I go back to this image, I theoretically could get rid of the collar part or the top canister part, and this gap would be infinite. And the canister would still slide. Granted, the water would leak out everywhere and this would not work for the device, but that is independent of this. That's actually a completely different requirement. The canister must hold and retain X amount of volume or fluid of water. So back to this, right? So now we've established the upper spec limit and the lower spec limit, and the spreadsheet will automatically calculate what is your CP upper and CP lower, and then give you the resulting CPK. But if we go back to our table and trying to establish what is our definition of done, we go through of like, hey, if the canister doesn't work, this is fairly serious. It means the water won't get to the pump, the device will not function. And so that puts me in my head as the design engineer, that puts me in the serious column, not from a risk of hurting the end user, but just a risk for the business and a risk for the product not being successful. So then I go down and say, okay, what range would put me in the teal zone? Okay, that's a CPK of 2 or greater, or what range would be, hey, as low as possible. So through my tolerance stacks and through these calculations and the equations above, I can see that I ended up with the CPK of 1.58. That puts me down here. That puts me into team review. So based on this, I could go to my team and I could say, hey, I want to move forward with a CPK of 1.58. Is that cool? Or I could say, okay, what do I need to change to actually get me to the green zone or to get me into this kind of yellow, lighter yellow-orange zone? Sorry, mailman's coming, so I can hear my dog bark. Give me 2 seconds. Get him. All right, there you go. She's ferocious. Okay, so now moving back. So what you can do then is after you've kind of finagled with your tolerances, you may see that like, hey, this just isn't reasonable. I can't expect to hold microns or to the nth degree precision on this part. I need to make a design change. And one of the ways to do this is using the equation for your CPK that's limiting you and solving for what the nominal gap needs to be. So in this equation, you can see that it is for upper, it's your upper spec limit minus your nominal divided by 3 sigma. And CPK lower is the inverse of that, basically. Nominal minus lower spec limit divided by your 3 sigma. So I take my CPK that I want to get to 1.67. I have my standard deviation, which was in this previous slide over here, right? I go back to that, I plug that in, and I solve for what my nominal needs to be. And once I've solved for my nominal, to hit a 1.67 CPK, I need to have a nominal clearance of 0.264 versus previously my nominal was 0.25. So for 0.015 millimeters, I can achieve as low as possible. I could also rerun this calculation with a CPK of 2 and say, what does my nominal need to be? Which I believe was like, I did this in the article, it's around 0.3, I believe. So once again, for 0.05 millimeters, I could make a design change right now and basically eliminate this error from ever happening. And so now this is where I really say is you're getting into predictive design, because you've gone through and used very simple equations to potentially eliminate tons of work, tons of failure modes, and tons of items that would be passed to subsequent teams, all with a 0.5 millimeter change, or not even a 0.5 millimeter, 0.05 millimeters, right? And so that is the power of what doing these tolerance stacks can do for you, is you can take something that seems relatively complicated, but once you put it all down on paper, it's simple addition, subtraction, and it's giving you insight of how risky is my design. Plus, at the same time, because you're following this method, and you go to here and you go to your tolerance stacks, these dimensions that are showing up in your tolerance stacks, the method to control them is to put them on your drawing. And now you're not, so I've done it multiple ways where I've just started like picking things on my drawing, like, yep, that's important, yep, that's important, yep, that's important. And over time, as the design engineer, you kind of become desensitized to that, and you just say, everything's important, and you just go hog wild, and you end up with like 30 critical dimensions on your drawing, which is great and easy for the mechanical engineer, but when you pass that to your partner, who's your manufacturing engineer, they're gonna come back to you and be like, really? 30? Dave, that's way too many, get a grip. And you need to have a method to say, yep, I need to pare that down into something that's more reasonable, which I would say for component design or in small things, 5. If you're doing a huge chassis or something that is a lot of interactions, you may end up with substantial more than that. But it's a matter of what do I want to boil it down to be measured, to be controlled in my manufacturing process, and why. And your risks and your risk hazards are what have guided you to this method. So this is more of a method of how do I use my tolerance stack to reduce my risk hazard situation and then put it in control via my drawing. And then as an added bonus, we did that. As an added bonus, you're also not over tolerancing your part. You have very explicit reasons for why this dimension gets this tolerance. And when you do that, it makes it easier for you to go to your boss when they're like, this part's way too expensive. And you're like, yes, I understand it's expensive, but this part is the key to the kingdom. It has 36 interfaces. It has this much influence on all of these different things. This is why I want to hold this tolerance stack so tightly. So I've been talking a lot, and it's probably a lot of information here, but I want to recap all of this also with kind of a flow chart of how you would make a decision on this. So if you go to this flow chart, you can see I've added another thing of what is CTQ, and CTQ is critical to quality. It means that this is a item or a feature that is basically important to the end result or the use of the product or the success of the product, etc. And you can flow through this of saying like, okay, if it's related to CTQ or a risk, I can follow the flow chart. And then as you go through and measure this, you can determine, do I need to make this a critical dimension, right? So not all of your dimensions that are in your tolerance stacks will be critical, but they should be on your drawing. I'll let you guys digest that for a little bit. Looks like we're doing fairly well on time. So feel free to ask questions, and if you need to, we can go back and address any of them as we're going. So kind of in summary, I'm not going to read this entire flowchart for you. I'll let you guys do that on your own. But in summary here, one of the things that you want to consider and keep in mind when you're doing your tolerance stacks is, do you have multiple configurations or positions to evaluate? So I did this very briefly in the linear rail where I kind of divided into subsystems, took a cross section, and then looked at just one interaction. There are many extremes for where you need to look at interactions, and the interactions aren't always stagnant. They can move, right? You're designing a mechanical system. There's buttons, there's springs, there's levers. And what you want to do is look at those positions and look at the different extremes. I want to look when the lever is fully up. I want to look when the lever is fully pressed. That helps me understand the limits of my design and also the different failure modes that can occur at the extremes of those positions. Another example that I've seen, and I've been a victim of this too, is to check your measurement configuration inside your SolidWorks. When you're using the ruler, there's options to do max and there's options to do min distance between like the two planes. And you want to make sure that when you're doing your analysis that you're measuring what you want to measure. Especially when you get into injection molded parts, there is a lot of stuff that happens where you've added draft. And so before, when you were seeing the part 0.25 was two straight lines, and then all of a sudden you've added the draft. And so now, yes, at the top where my thumbs are, if you can see the image, that may still be 0.25, but because I've added draft, my pinkies down below are now below that limit. And that can completely change your tolerance stack where you thought you had ample clearance, but now that you've added 1 to 3 degrees of draft, you are eating all of that clearance up in just your draft. And so it's very important to measure that and confirm that. And then even sometimes on your drawing, go a step further and very explicitly say, please measure at the top of my draft, or please measure at the bottom, and make sure that the correct dimension is actually on your drawing. And then lastly, a good example of this too is like, am I controlling things way tighter than it needs to be? And the answer is generally, I would say on a lot of the drawings I see, this happens a lot. And this goes back to the numbness of creating the drawing and just being like, boom, boom, dimensions everywhere. And that's because a lot of this process does take time, but it is very useful. And so the last thing I would say is like, not only does it help you reduce cost of your part, it also helps you provide a framework and a recipe book that many teammates can review, jump in, see what you're talking about. And it also can be used as a very successful root cause analysis tool, because this will happen. You will get some of your tolerance stacks wrong. There are other things that can happen outside of the strict math of the tolerance stack that can cause assemblies not to work, right? So mechanical engineering failure modes, right? It's either moves and it's supposed to, or it doesn't move and it's not supposed to, right? So it's either WD-40 or duct tape. And that's a kind of old engineering joke of what are the two tools to how to fix stuff. But using that information of, hey, if it's moving or interacting and it shouldn't be, what is happening? Is it just the design where the tolerance is just incorrectly done? That's step one. And usually it's beyond that. Hey, is there a thermal boundary condition? Is there something else that is happening on my system that is not measurement related? And this whole method here is about how do I control that risk and how do I establish, is there another risk that I missed? And this to me, tolerance stacks is like stretching for a sporting event or warming up, right? This is a big foundation that you set of all of the rules and all of the things that were in your head as you made decisions, right? There's all these books about don't make more than 3 decisions in a day at a high level, but in engineering and a lot of these decisions, you are making a ton of decisions as you just decide, how do I want to extrude this feature in SolidWorks, or what am I thinking at the time? And these tolerance stacks and the method of providing your upper and lower spec limits puts you in a position where you said, I made this decision and I made this choice because, and it's rooted all the way back into performances of the device, risk of that device to a customer, or a method of saying, I know I did this by laddering up through the different systems, which many engineers don't do. If you were to read my article, I would say most people look at tolerance stacks as a very simple, will my parts fit, yes or no? But doing further analysis of saying what can go wrong, why can it go wrong, and then what are my limits that make wrong or right happen, gets you into predictive design and leads you to a CPK type of calculation that will enable you to control your design and potentially eliminate bad features from the get-go, such that later on you just never even see it. And that's really where you want to be. A good mechanical engineer, most people don't know because it just works. It's when it doesn't work that all of a sudden people are like, what'd you do? Why is this happening? What? And then you want to be the prepared one that says, boom, here's stacks and stacks and stacks of calculations that I've done to prove that this will not happen. Okay, that is all I have for now.
Well, thank you so much, David. Great presentation. I think this hit home for a lot of our attendees today. A popular comment in the chat was, when did you learn how to do stack-ups? I know I personally learned on my first job and through senior engineers. So this is probably a topic a lot of young engineers don't learn directly in school. So I think it's a great conversation we're having.
So you want me to answer that?
Yeah, go ahead.
Oh, yeah. So I personally, obviously learned tolerance stacks in school as well. I was also a TA and did a bunch of, I think I taught GD&T and CAD and stuff for, I don't know, 2.5 years-ish. So very familiar with that. And then this whole method that I just described to you kind of got brought to me through industry. And as you can expect, like I was just highlighting the basic accounting, right? Like tolerance stacks are like balancing a checkbook. Then there are the subsequential branches that can come off of this, where say you're doing gaps and you're like, hey, if the gap is below 1 millimeter, I want to do some type of FEA analysis to prove that the thermal elongation of my externals on my jet engine don't cause a vibratory or interaction with something else. And so using this framework, you can start setting up limits for what other type of work is required to manage a risk. And that I did not learn in school, which is why we have this whole presentation, because I was like, that's interesting to me.
No, and extremely valid. So we have a couple of questions already in the Q&A. If you'd like to submit a question, please type your question to the question window on the side of your screen and hit the submit button. David, our first question is, how does GD&T controls influence the tolerance stack calculation workflow?
So if you were to, sorry, I'm trying to click this through, trying to expand the thing. So the GD&T, so what's really important, and this is a subtle nuance in many of, and almost all of the tolerance stacks, is that you want to come back to a datum. And what I mean by this is there ability for me to draw?
I don't believe we have that ability currently.
Okay, that's fine. Okay, let's just use my hand as an example. So say when you go to use your GD&T, say I put my thumb as datum A, and I want to get from here to my pointer finger, right? If I did one dimension from here to my pointer finger, that's one tolerance, right? And I can go from the datum to my finger. If I tolerance this incorrectly, I went from here to here, so I went from one step and then here to here. To get back to my datum, I need to complete the loop. So the GD&T is important because it can limit the number of tolerances that are in your loop, or the number of dimensions. Does that make sense or adequately answer the question?
I believe so, yes.
Okay. And then the last one for the GD&T is just through experience. One of the things that I've noticed that influence my tolerance stack greatly, especially in 3 dimensions, are alignment pins. So just the perpendicularity of your alignment pin, it being slightly off, depending how long that part is, right? Law of cosines, right? It's like, or small angle theory. You can end up with just very small alignments of your pin being off, causing interactions that are much further downstream, all because this pin is not perpendicular. And then lastly, on the GD&T, yes, like I said, it's important, and a lot of your GD&T is actually telling your inspector how you want to inspect that dimension. Cool.
Excellent. Our next question is, and we have a couple of these, so can you please review the Cpk calculation again? And am I supposed to shift to my normal dimension during the calculation? We also have a few people who've asked if you can go back to the slide that showed the Cpk evaluation.
Okay. Yep. Let me make this a little bigger. Come on. Sorry, guys. All right. can everybody please see the slide?
Yep, we can see it.
Okay, so this is the tolerance stack here. And so what I believe the question is when I do the CPK analysis, what do I use as my nominal?
Yes.
So the nominal comes from your CAD, right? So in this example where I am calculating this gap, my nominal gap is 0.25, and that is what is used to determine that the CPK for this specific example is 1.58. So if you were to plug in all of those values, you would get this. And then when you are adjusting your nominal, right, when I say, hey, 1.58 is not good enough, how do I get to a CPK that's in my green or yellow zones? Then you back calculate. You plug in your desired CPK, which was 1.67, and you're solving for your new nominal. Your lower spec limit was 0 in this example, and your 3 sigma, your sigma came from the previous slide, push to audience, the standard deviation down here, listed here in the bottom row purple on the right.
Excellent. Our next question is, do you consider inspection measurement uncertainty, inaccuracy, and repeatability in some way?
So in all simulations or all calculations, garbage in is garbage out. So this depends where you are in your process and where you are in your design development. As an initial step back to, hey, like why GD&T is important, why setting up the datums, yes, you need to consider that, but that is a pre-filter for how those numbers get into your system. When your first go around, you're going to determine that, yes, that the measurement system is capable, that the ability and the tools being used to measure are good. As you go further along, you may discover that, hey, this isn't working, even though my math said it should. Now you're looking at your inputs. You're saying, I am thinking about it this way. How are they doing it? And back to the steps, like, because you have your tolerance stack, you very clearly laid out a list of sequential steps that you believe are happening. And if it's not coming true, then that means one of your assumptions are likely incorrectly for what's really happening. So it is important, and this is not necessarily a single static process. You may do this and pass your EB build or whatever, and then say, hey, I need to do this again. And now you're going to actually use some CPK analyses or some capability analyses from your suppliers to backfill these calculations, because not everything will come out perfectly. There might be some dimensions which your supplier comes back and says, David, that's just not doable, man. I can't hold plus or minus 1 micron for you at this big dimension, but I can hold 5. And then you may go to another part where they said, oh, you said plus or minus 5, not a big deal. The CPK analysis results are actually showing that we can hold plus or minus 2. And then you would adjust your tolerance stacks to kind of account for the budget of this, and now track what is actually happening.
Excellent. Our next question is, can you comment on using RSS versus worst case?
Yes. So RSS, so if you wanted to go into that article, it will, one of the kind of resource articles, it will very in-depthly describe this. But worst case scenario, doing a max min, that is okay for like 2-part fits. But as you get more and more parts or more dimensions added to your tolerance stack, doing worst case analysis is super conservative. It basically means I believe that the worst case edge of my, let me go see if I can find that. Let me go back to this. Push the audience. Okay. Somebody could mute real quick. That'd be great. Okay. So when you do worst case tolerance stacks, you're assuming that everything is happening at your lower spec limit or your upper spec limit of a single part. So you're saying that the smallest and the smallest and the smallest and the smallest are all interacting with each other. And that is statistically improbable. It is not probable that you will get the worst of the worst of all of your parts to be miraculously put together, and that's what will happen. Usually it is a distribution. You may get one part that's skewed to upper, and you may get another that's lower, and you get one that's in the middle. And so when you're actually utilizing the randomness and the variability of your parts to say that this is actually less improbable than trying to do min-max worst-case tolerance stack situations.
Great. Our next question is, for a lot of people have been asking for some clarification on some numbers within the risk chart that you showed. Could you explain those ranges and how are they used?
Gotcha. So from this, CPK relates to the probability of risk. So on the left-hand side, these are just your CPK thresholds, right? That is how likely am I able to park the car in the garage, right? Below 1, it means you are crunching the car. Above 1 means you make some clearance, but there's not a lot of right to left room. And then 1.67, 2 or greater is like, hey, you can come in hot with your car and you're not going to clip a mirror off, right? That's what that means on the left-hand side. The top vertical axis, right, obviously relates to the risk or the hazard that you're trying to eliminate. And then the numbers inside these charts are what percentage contribution does that single dimension have to my overall tolerance stack loop. And these are suggesting that if your single tolerance provides 25 to 35% of it as a contributor, that you should make it a critical dimension. And that means you should have a quality inspection plan for how to control that dimension through the life of your product, such that the risks that you've identified don't come to fruition. So if it's 20, so this gold kind of yellow color here, if a single dimension is between 25 to 35% of your contributor for a critical, you would make that a critical dimension. If it is 45 to 55% for a moderate failure at a CPK of 2, then you would make that a critical dimension. So these numbers on the inside of these this chart here are much more aimed towards if you were to do some type of CTOL or VisVSA, three-dimensional tolerance stack analysis software. Those softwares give you the contribution numbers out. And this is just a metric or a method for how you say, yep, this becomes a critical dimension. Obviously, when you're doing RSS, they're not all like, it doesn't go through and say, this one contributes this much, this one contributes that much. They're all considered to be equal. And that's where your subsequent measuring CPK, GR, and R of single parts becomes very important. Great. Any other questions?
Sorry about that. I had myself on mute. We have time for one more question before we wrap up here. Given that CPK process capability, what method would you use in the design stage when the process capability is not known?
Gotcha. So when the design process capability is not known, I would still utilize this method because it gives you a benchmark for what you want to push for and why you want to push for it. Like I said, doing min-max is super conservative and basically can design you into a corner. Where if you're trying to solve all of those, it's really, really hard to balance all min-maxes, which is why, like I said, you want to be in the green zone as much as possible, but that's also why this yellow zone exists, because there's a reality of when I'm trying to balance every single thing, that it may become difficult to achieve 6 sigma or CPK of 2 or greater for every single tolerance stack that you look at. And depending on what risk it is, you might actually say, you know what, I'm way better and I think it's way more reasonable to make this 2-part fit overtly tight and maybe break on the assembly line at an acceptable scrap rate versus making this one feature slam dunk. I can, dunk it and pass that step of the assembly process all along, only to discover later that that loose pin is affecting the parallelness or the parallelity, if that's a word, of my assembly such that it's now not working.
Well, that was great, David. Thank you so much for your time today and your presentation. It was wonderful. I think a lot of information was shared today.
Thanks, guys. There is a lot of information. If you have any other questions, feel free to reach out to contact myself at Fictiv or our team, and we can definitely help you with any of this or further explanation. There's also an article if you would like to read that, and it probably supplements or goes along with this really well. Thanks, guys.
Yep. So thank you, everyone, for attending our event today. To learn more about Fictiv and to get an instant quote for precision machine parts, visit fictiv.com. Getting started is as easy as creating a free account and uploading your 3D CAD and 2D drawings for an instant quote with DFM feedback. Fictiv has manufactured over 12 million parts for startups and enterprises alike, specializing in precision, tight tolerance machine parts for robotics, medical devices, aerospace, and automotive industries. You can also read more on this topic in the deep dive article on Fictiv's Resource Center. You will also include a free tolerance stack calculation workbook that you can download. You will see a link into the article into the chat here, and you'll receive an email following this webinar from Fictiv with a link to the slide deck, article, and workbook as well. If you missed any part of this presentation, it will be archived shortly, and so you can view it again, refer someone to it, or access those related materials. Again, thank you, David, for your time, and to everyone, have a great afternoon.
Thanks, guys. Bye.